It talks about an object coming into collision with a satellite. The object is this space junk, and they give a radius and mass for our satellite. We got radius 4.9 meters and mass 195 kilograms. It gives a velocity for the satellite, so the satellite is moving forward with 3,000 meters per second. It also gives an angular speed of the satellite being 2 radians per second, and it's rotating apparently clockwise, so that's a negative angular speed. They say that the mass of the space junk is 3.9 kilograms, and it has a velocity of negative 2,100 meters per second. It says the space junk will hit the edge of the satellite and move off with a new velocity. Before and after the collision, don't worry about the rotation of the space junk. So first they ask for what is going to be the final momentum of that satellite. Alright, so first of all, we have to figure out what momentum the space junk is going to have. So let's find that. It'll be Pi equals m times Vi. Alright, so initial momentum then of the space junk will be found by multiplying your mass times your velocity. So let's get that. I get negative 8190. This will be kilogram meters per second. I'm going to find the momentum of the satellite as well. So I'm going to call the junk object B, I guess. And then we'll come up with a momentum for our satellite, which could be PA, momentum A. So we need the mass of the satellite times the velocity of the satellite. Okay, so that's going to be 195 kilograms times 3,000. So why am I finding the momentum? Because we have to have conservation of momentum in this collision. Keep in mind, though, that this is linear momentum. So I get 585,000. That would be kilogram meters per second. Okay, now what we should also do is let's find the angular momentum of the space junk about the satellite, and let's find the angular momentum of the satellite too. So you have to pick a point about which you want to calculate the angular momentum, right? So I'm going to pick the center of the satellite as my pivot point, P. Now I could find the angular momentum of the space junk about that point P, and here's how you do it. You have to come up with a lever arm, which is a distance away from your pivot point P. It's perpendicular, though, to the direction of motion of the object in question. In this case, the space junk is moving not directly at pivot point P, but it's moving around it. So it could be said then to have angular momentum, you just have to know that distance r, and then we can use angular momentum formula for the space junk. It will be L equals r cross P. So our distance is the radius of the satellite, 4.9 meters, and our momentum of the space junk is 8190 kilogram meters per second. Now when it comes to the direction, you have to use a right-hand rule here. Your space junk is going about pivot point P this way. So that would be counterclockwise. Even though it's not rotating around, it still has angular momentum. So let's make that clockwise, which is positive. And I'm also going to assign a letter that you might not have seen before, K hat. Okay, so why would I be calling it K hat? Because if you use the right-hand corkscrew rule, where you curl your fingers in the direction of motion of your space junk, then your thumb would actually point up. Okay, so thumb points out of the page. And so out of the page is considered the k-hat direction. So let's do that. We could also find angular momentum of our satellite, which is going to be a different approach. He is a large rotating body, a sphere, so I'm going to use the formula I omega for that. We know his moment of inertia, we can calculate it. So a sphere from the formula sheets has a moment of inertia formula of 2/5 mr squared here. Solid sphere rotating about center. So let's use that. His mass was 195. His R was 4.9. And then his rotation was 2 radians per second. He is rotating in the negative direction though, so we have to take that into consideration. And just to be clear, like what I did there, I used the formula 2/5 mr squared times omega, where this is the mass of the satellite. Okay, so let's calculate what that angular momentum is. I get 3746, and then we'll calculate this guy as well. 40,131. Okay, so these are the initial angular momentums of our objects. They ask us in the question to analyze both momentum and angular momentum. So they want us to find the final linear momentum of that satellite. So we have to have conservation of linear momentum. So let's take into account all the momentums that were present at the start, like before the collision. The junk was moving with 8190. The satellite was moving with this much momentum. So that's going to be the sum of our initial momentum if we add them two together. Alright, so I would do it personally in like a component form. So let's do this, that our satellite was moving with 585,000 and y component of 0, and then our junk was moving with negative 8190 and a y component of 0. So they're both moving in the x dimension initially, and that's all the linear momentum that we have at the start. Now we have to set that equal though to the final momentum. So this was the satellite and this was the junk. Alright, so what is there at the end? Well, here they talk about the final velocity of the junk. So we really need to take that and turn it into a momentum. We're going to have an unknown final momentum of our satellite. So let's do this. Leave this as unknown. But what we do know is we do know the junk final momentum. Okay, so let's multiply the junk's mass times his velocity there. His mass was 3.9 kilograms. So I'm just going to multiply the 3.9 times his velocity components. Alright, so that kind of approach will allow you to solve for the final components of momentum, right? I can do it very easily with an online calculator, such as Symbolab. Okay, so all I'll do is I'll treat the x and y components separately here. So let's say 585,000 plus negative 8190 has to equal an unknown variable plus 3.9 times negative 1100. All I'm doing, of course, is I am combining this x with that x and that x and that as well, just doing all the x components together. So I get 581,100 for the x component. Now I'll solve for the y. It's negative 1911. Okay, keep in mind these are kilogram meters per second units. Okay, so this is what I would put here. Let's see, negative 1. and then just put a 0 for the z dimension. Okay, then we could easily find the velocity just by dividing. So my velocity final will be 581/100 divided by the 195, I guess it was, for his mass of the satellite. 2980, 9.8, and 0. So your Li is going to be a sum of these guys. So 40,131 minus 3746. I get 36,385. So you would actually put that here. And these would be 0 because the angular momentum is a pseudo vector. It's perpendicular to the original vectors. If they're in the x and y dimensions, then the angular momentum has to be in the z dimension. All right. All we have to do is just figure that the final angular momentum has to equal the initial. Okay, we have to have conservation of angular momentum. So you just do the same kind of thing. Your sum of Li has to equal your sum of Lf. We already have the Li. And they gave us the final speed of that space junk. So we could find his final angular momentum about the pivot point P. So what's his new angular momentum? I'm going to let this guy be LA final. That's the satellite. And then for the junk, you just have to do R cross P for the junk. Okay, then you could finally solve for the L, Okay, so we're actually going to put the initial angular momentum of the satellite into these boxes. Now we do have the option of extending the path that the junk is taking back and then creating a perpendicular with that path that touches point P. And as long as it's a 90-degree angle, then this could be used as the new R that we could multiply by P. However, that's not really super effective here because it'd be very difficult mathematically to quantify exactly how big R is, so I'm not going to use that approach. Instead, what I'll do is I'll do a cross product between the existing R here and the momentum of the junk. So the momentum will be P, and I can use the existing R that we already used, but we do have to know the angle between the R and the P. So that's going to be our next task. We already know the final momentum of the junk. It was given earlier. Yeah, this was the final momentum of the junk. 3.9 times negative 1100 and 3.9 times 490. Let's simplify that. Okay, so we have the linear momentum of that junk. We can also put this R vector into a component form as well. As a component form, he's going to be 0, 4.9. That's because the distance is 4.9, but he's oriented vertically, which means that we would make that 4.9 his y component. His x component is 0 because he's not pointed in the positive x or negative x direction at all. We can now take these two vectors, this one and this one, and we can do a cross product on them to find the final angular momentum of the junk. Okay, now there is a shortcut formula for doing a cross product like this. It's one option to just use the components. The shortcut formula would be, if you want to do a cross product of A cross B, you could do AX BY minus AY BX. So we do have that option. We could simply use RX PY minus RY PX. The other method that might be used would be to get the actual angle between the vectors. That could be done with the components of it. So if I find a reference angle for the momentum with a tan inverse, so I get 24 degrees out of that. So that is going to be a reference angle that would be located here, and we of course have 90 degrees in this part of the angle. So our theta then would be 24 plus 90, or 114 degrees. So if we didn't want to use this approach for the cross product, we could use this one. So it really just depends on, which way you want to do it. So I'll do both ways. For Rx, we'll have 0. Rx was 0. Our Py component is going to be 1911. Ry is going to be 4.9. And then Px will be the negative 4290. So it's about 21,000. It will be positive. And this angular momentum would be positive because the space junk is rotating in such a way that it's thought to be going counterclockwise relative to point P. If we try the other formula, let's see if we get the same answer. We would have to do Rp sine theta. P is our magnitude of momentum. For that, we're going to need a square root of px squared plus py squared. These are the final quantities for the junk. And then we'll do sine of 114 degrees. Okay, so let's see what the components of the momentum are. Negative 4290 and 1911. Okay, so using this approach with this formula, I get 21,020 or so. So both approaches clearly can work in this situation. So we will now put 21,020 as our final angular momentum of the junk. So this will allow us to find the final angular momentum of the satellite too. So let's see if we can answer the questions here. Which of the following statements about the translational angular momentum of the space junk about location D are true? Is R perpendicular the same when the space junk is at locations A, B, and just before getting to point C? That is true. the r that we're using to calculate the space junk's angular momentum actually doesn't change as the space junk proceeds forward toward the satellite. So whether it's at A or B or even right before the collision, the object has the same velocity and it has the same radial distance perpendicular to the path of travel. Because the space junk is traveling in a straight line, its angular momentum is 0. No, that's not true. Because the space junk is moving not directly at point P, but around it or past it, that actually does allow us to calculate angular momentum for the space junk. The translational angular momentum of the space junk is the same when it is at points A, B, and just before C. That is true. We saw the calculation earlier. Yeah, the calculation is just R cross P. The P is going to remain constant, and the R that we use as like the leverage arm is the same. If we do xpy minus ypx, would that quantity be the same when the space junk is at locations A, B, and just before C? So what it's referring to there is the formula for cross product, that if we have two vectors being crossed, we can use the formula ax by minus ay bx. The vectors in question here are r and p, and so we have rx py minus ry px being the way that we calculate angular momentum. So rx and ry can be rewritten as just x and y. And so is it the same no matter where the junk is located, A, B, or C? It would be the same. Is the translational angular momentum of the space junk in the negative z direction? That's not true. I showed that earlier when I calculated the angular momentum using the right-hand rule. The thumb here points out of the page, which is the positive z direction. So if we have positive x being to the right and up being positive y, then the z points out of the page toward the viewer. The z here is the thumb, which points at us. Okay, now we have to fill in the initial angular momentum of the junk. That was calculated, that would be this calculation here that had been done for the space junk. So this is our angular momentum initially for the space junk. It was moving quite fast, so it has a pretty large angular momentum. Now let's put in the final angular momentum of the junk. The final angular momentum of the junk was calculated here when we did r cross p for after the collision. Now it wants us to enter the satellite's final angular momentum. So let's now do the calculation for the satellite. The way I'll find that is by letting the sum of initial angular momentum, set that equal to the sum of the final angular momentum, where this was just the junk, and this was the angular momentum of the satellite, which is unknown. I get 15,362 kilogram meters squared per second, and that is for the satellite. Now the question asks for the new angular speed of this satellite. I'll use the formula L equals I omega, And we'll apply this to the final quantities for the satellite. I'll use his moment of inertia from earlier of 1873 kilogram meters squared. So I get 8.2 radians per second for the final speed, and this is a positive value here. So the satellite used to be having a omega which was clockwise, and because I got a positive out of this calculation, that means he is now going to be rotating counterclockwise. So he was going clockwise, but the junk had so much angular momentum here that it caused the satellite to switch the direction of rotation. Now it's going to be rotating counterclockwise in the end. Lastly, the question asks about energy for this system. The question wants to know, what was the total kinetic energy considering translational and rotational energies at the beginning before the collision? So I'm going to add up the K of the satellite, and this is going to be linear kinetic energy. This is going to be due to translation, and then we'll also add the kinetic energy of the satellite due to rotation, because we can have both types. This will be for the satellite, and now we also have to do the same for the junk. Okay, so translational kinetic energy formula would be 1/2 mv squared, and we'll do this for the satellite. So that was object A. For rotation, we would have a formula of 1/2 I omega squared. The junk can also have translational kinetic energy. When it comes to the rotation, though, they stated in the problem to consider the rotation of the junk to be negligible. So I'll just leave that as a 0. All right, let's plug in all the quantities. 195 kilograms satellite moving with 3,000 meters per second. Let's plug in that moment of inertia of the spherical satellite, which was 1873. Okay, that there should take care of the energy of the satellite. Now let's get that energy of the junk. Speed of 2100 meters per second. And we'll calculate that. So I get 886 million joules for the sum of initial kinetic energy. And now they ask, after the collision, what will be the total kinetic energy of this system? Okay, so we're going to do the same kind of thing. But we'll now use the final quantities. To get the final speed of the satellite, we're going to have to use his components. So much earlier, we had found these to be the final components of momentum for the satellite. And then we used those to find the final velocity. Let's just calculate these real quick. Yeah, so looking at the final velocity of our satellite, his components are 2980 and negative 9.8. So those can now be used and we can get his final speed plugged in. We determined his final angular velocity to be 8.2 radians per second. And for the junk, we'll again use his final components of velocity in the calculation. The final velocity of the junk was actually stated in the problem. Negative 1100 and 490 were his components. Let's calculate that. $869 million joules. Okay, now it says, what would be the rise in thermal energy for the space junk and satellite combined? And so if we assume that all the losses in energy go to thermal energy, then we'll just find the difference between the final and initial kinetic energies to find the loss. I get that there was a loss of 17 million joules. And so I'll say that the change in thermal energy will be the same.